Something impossible is happening right now. At this very moment, approximately 450 million miles from where you're sitting, an object from beyond our solar system is doing something that shouldn't be possible. It's interacting with our sun in a way that challenges everything we thought we understood about how the cosmos works. The data is there, the measurements are confirmed. Multiple independent observatories have recorded the same phenomenon. And yet, when you really think about what it means, when you let yourself consider the implications, it becomes one of the most profound mysteries in modern astronomy. Welcome to the sleepy cosmos. The object in question has been designated 3I divided by Atlas, and it arrived from the depths of interstellar space sometime in the last several months. It's the third confirmed interstellar visitor we've detected passing through our solar neighborhood, following the now famous Oumuamua in 2017 and the comet 2I divided by Borisov in 2019. But unlike those previous visitors, which simply passed through our system on their lonely trajectories across the galaxy, 3I divided by Atlas is doing something different. Something that has astronomers around the world staying up late, rechecking their instruments, and having quiet conversations in observatory hallways about things they never expected to see. The sun is losing energy, and 3I divided by Atlas appears to be where that energy is going. Now, before you close this video thinking we've gone full science fiction, let me be clear about something. The data we're about to discuss comes from some of the most sophisticated instruments humanity has ever built. The Solar Dynamics Observatory, the Parker Solar Probe, ground-based coronagraphs from Mauna Kea to the Atacama Desert, radio telescopes scattered across multiple continents. These are not fringe instruments operated by amateur enthusiasts. These are billion-dollar missions staffed by thousands of the world's leading astrophysicists. And they're all seeing the same thing. Let's start with what we know for certain, and then we'll work our way toward the edges of understanding, where the mystery really begins. 3I divided by Atlas was first detected on March 14th of this year by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, which is how it got its designation. At first, it appeared to be just another long-period comet, probably from the Oort cloud, following one of those vast elliptical orbits that bring icy visitors from the outer reaches of our solar system every few centuries. But within 48 hours, something about its trajectory didn't add up. The orbital calculations kept producing numbers that didn't fit any reasonable elliptical path around the sundial. Its velocity was wrong, its angle of approach was wrong, and most tellingly, its radial velocity, the speed at which it was moving either toward or away from us, indicated that it wasn't bound to our sun's gravity at all. It was passing through. A visitor from another star system, on a trajectory that would eventually carry it back into the infinite dark between the stars. This alone would have been enough to make 3I divided by Atlas a major astronomical event. Interstellar objects are incredibly rare detections. Think about the scale for a moment. Our solar system is enormous, stretching billions of miles from the sun to the heliopause where the solar wind finally gives way to interstellar space. But in galactic terms, it's a speck, a tiny bubble in an ocean of emptiness. The odds of any object from another star system happening to pass through our solar system at exactly the right time for us to detect it with our current technology, in our brief moment of having that technology, those odds are astronomically small. And yet, here we are, having detected 3 such objects in less than 8 years, which raises its own questions. Questions we'll return to later. But first, let's talk about what makes 3I divided by Atlas so different from its predecessors. Oumuamua was strange enough. That cigar-shaped object tumbling through space, exhibiting non-gravitational acceleration that still hasn't been fully explained. The scientific community eventually settled on outgassing as the most likely explanation, though even that required some creative physics to account for the complete lack of any visible coma or tail. And the shape itself, at least 10 times longer than it was wide, was unlike any comet or asteroid we'd ever seen. It sparked debates and speculation that continue to this day. 2I divided by Borisov was more conventional. It looked like a comet, acted like a comet, and aside from its interstellar origin, didn't present any major mysteries. It was almost reassuring in its normalcy. A reminder that the universe, for all its strangeness, generally plays by the rules we've discovered. But 3I divided by Atlas is different. It's approximately 2 kilometers across at its widest point, based on spectroscopic analysis and brightness measurements. That's significantly larger than Oumuamua, but smaller than many comets we routinely observe. Its surface appears to be composed of materials consistent with what we'd expect from a comet: water ice, carbon dioxide ice, various organic compounds, and silicate dust. Nothing exotic. Nothing that screams mystery object from the stars. What's strange is what happened when it entered the inner solar system, that region inside Mars's orbit where the sun's radiation becomes intense enough to start sublimating frozen volatiles from a comet's surface. Normally, this is when a comet becomes most visible and most spectacular. The ice vaporizes, creating that characteristic coma, the hazy cloud surrounding the nucleus, and the pressure of that vaporization, combined with the solar wind, creates the magnificent tails that have inspired humanity for millennia. We can predict this behavior with remarkable accuracy. We know what chemicals will vaporize at what distances from the sunday. We know how bright the coma should be based on the comet's size and composition. We've been observing comets for centuries, and in the modern era, we've got the physics down to a precise science. 3I divided by Atlas developed a coma right on schedule as it approached the sunday. But something else happened too. Something that wasn't in any of the models. The Solar Dynamics Observatory noticed it first, though at the time, no one made the connection. The SDO is a NASA satellite that observes the sun constantly across multiple wavelengths of light, from visible to extreme ultraviolet. It watches the sun's surface for sunspots, flares, coronal mass ejections, all the dynamic activity that makes our star a roiling, magnetic storm of plasma, and is very good at what it does. It takes images of the sun every few seconds, building up a continuous record of solar activity that has revolutionized our understanding of solar physics. On March 22nd, 8 days after 3I divided by Atlas was discovered, the SDO recorded something unusual. A localized dimming in the sun's extreme ultraviolet output. In a region of the corona, the sun's outer atmosphere that happened to be oriented in the general direction of 3I divided by Atlas's position in space. Now, the corona is always fluctuating. Bright points appear and fade. Coronal loops form and collapse. The entire structure is constantly shifting and changing as magnetic fields twist and reconnect. But this dimming was different. It was more stable, more persistent, and most peculiarly, it seemed to track across the sun's face in a way that maintained a consistent angular relationship with 3I divided by Atlas's position. At first, it was written off as coincidence. Space is big, and when you're looking at the sun, there's always a direction from the sun that points towards something. A planet, an asteroid, a distant star geometry alone ensures that alignments happen constantly. They're meaningless. But then the Parker Solar Probe picked up something similar. The Parker Solar Probe is one of the most ambitious space missions ever attempted. It's literally flying through the sun's corona, closer to our star than any human-made object has ever ventured, protected by a cutting-edge heat shield that keeps its instruments cool, even as it endures temperatures exceeding 1,000,000 degrees. Its mission is to study the solar wind, that constant stream of charged particles flowing out from the sun, and to understand the mechanisms that heat the corona to temperatures far exceeding those of the sun's visible surface, which is one of the great unsolved puzzles in astrophysics. On March 25th, during one of its close passes, the Parker Solar Probe detected an anomalous depletion in the solar wind's density and velocity, in a narrow cone extending outward from the sunday. The affected region was roughly 2 degrees wide, small in astronomical terms, but much larger than any known phenomenon could account for, and the direction of that depletion It pointed almost exactly toward 3I divided by Atlas. Now astronomers started paying attention. Within days, observatories around the world were retasked to study the phenomenon. Radio telescopes like the Very Large Array in New Mexico began monitoring the sun's radio emissions in the direction of 3I divided by Atlas. Ground-based coronagraphs, specialized telescopes that block out the sun's bright disk to observe the fainter corona, were pointed at the relevant region. Even space-based observatories, like the Solar and Heliospheric Observatory, or SOHO, joined the campaign, and they all confirmed the same thing. There was a real, measurable depletion of energy and particles flowing out from the sun along a vector that pointed directly at 3I divided by Atlas. Not precisely at its current position, but at where it would be by the time light and particles traveling at those speeds would reach that location. The phenomenon was tracking the comet's motion, compensating for the light travel time across hundreds of millions of miles of space. This is when things got really interesting, because this level of specificity, this precise directional correlation, couldn't be coincidence. Something about 3I divided by Atlas, or something happening in the space around it, was interacting with the solar output in a way that created a measurable, trackable effect. The obvious question is, how? How could a 2-kilometer ball of ice and rock, even an interstellar one, affect the sun across such a vast distance? The sun is massive beyond human comprehension. It contains 99.86% of all the mass in the entire solar system. Every second, it converts 4 million tons of matter into pure energy through nuclear fusion. The total power output of the sun is roughly 3.8 times 10 to the 26th watts. That's a number so large it's essentially meaningless to human intuition. You could power human civilization for 1 billion years on less than 1 second of the sun's total output. And yet, this tiny interstellar visitor, this cosmic snowball from another star system, appears to be drawing energy from it. To understand how this might be possible, we need to talk about what we mean by energy transfer in space, because it's more complex and more fascinating than simply one object taking power from another. Space is not empty. That's one of the most important things to understand about the universe. Even in the darkest, most remote regions between galaxies, space contains particles and fields. And within a solar system, the space between planets is actually quite busy. The solar wind alone ensures that. Every second, the sun ejects roughly 1 million tons of matter into space in the form of that wind, a supersonic stream of charged particles, mostly protons and electrons, flowing outward at speeds between 200 and 500 miles per second. This wind carries with it the sun's magnetic field, dragging those magnetic field lines out into space, creating what's called the interplanetary magnetic field. When something enters this environment, it interacts with it. Comets provide a perfect example. As a comet approaches the sun and begins to outgas, releasing molecules from its sublimating ices, those molecules become ionized, stripped of electrons by the intense ultraviolet radiation from the sunday. These ionized particles are then picked up by the solar wind and swept backward, away from the sun, forming the comet's ion tail, which always points away from the sun regardless of the comet's direction of motion. This interaction also creates what's called a magnetic pile-up region, where the interplanetary magnetic field lines pile up and drape around the comet's coma, like water flowing around a rock in a stream. This is normal. This is expected. We've observed this happening with every comet we've ever studied. But 3I divided by Atlas appears to be doing something more. Something that goes beyond passive interaction and enters the realm of active energy transfer. The key evidence comes from spectroscopic data, which is basically a detailed breakdown of the light coming from an object. Different elements and molecules absorb and emit light at very specific wavelengths, creating a unique fingerprint that astronomers can read to determine what something is made of and what's happening to it. When researchers analyzed the spectrum of light coming from the region around 3I divided by Atlas, they found emission lines that indicated the presence of highly energetic particles. particles with energies far exceeding what you'd expect from normal solar-wind interaction. We're talking about particles accelerated to near relativistic speeds, carrying energies typically associated with solar flares or coronal mass ejections. But there were no major solar flares or CMEs directed toward 3I divided by Atlas during this period. The sun was relatively quiet, and yet there was this population of extremely energetic particles concentrated in the space around the comet. Where were they coming from? How were they being accelerated? The current working hypothesis, the one that's being cautiously advanced in academic papers and conference presentations, involves a process called magnetic reconnection. This is a real phenomenon, well documented in solar physics, and it's one of the primary mechanisms by which the sun's magnetic energy gets converted into the kinetic energy of moving particles. Here's how it works. The sun's magnetic field is incredibly complex, constantly being twisted and tangled by the churning motions of the sun's interior. Sometimes, magnetic field lines with opposite polarities get pressed together. When this happens, they can snap and reconnect in a new configuration, releasing tremendous amounts of stored magnetic energy in the process. This is what powers solar flares and many other energetic phenomena in the solar corona. In a fraction of a second, magnetic reconnection can release the equivalent of billions of nuclear weapons, accelerating particles to extreme velocities and heating plasma to tens of millions of degrees. Now, magnetic reconnection typically happens on the sun itself, in the dense environment of the corona, where magnetic field lines are strong and closely packed. But it can also happen in interplanetary space, wherever different magnetic field regions come into contact. The Earth's magnetosphere provides a good example. When the interplanetary magnetic field carried by the solar wind encounters Earth's own magnetic field, reconnection can occur at the boundary between them, allowing solar wind particles to enter the magnetosphere and eventually creating the auroras we see at high latitudes. The theory being developed around 3I divided by Atlas suggests that something about its interaction with the solar wind and the interplanetary magnetic field is creating conditions favorable for enhanced magnetic reconnection. Perhaps the comet's coma, full of ionized particles, is acting as a kind of magnetic catalyst, locally changing the properties of the interplanetary field in a way that promotes reconnection. Or perhaps there's something about the comet's own magnetic properties, possibly a remnant magnetic field frozen into the material from its formation billions of years ago, in another star system that's interacting with sun's field in unexpected ways. If this is what's happening, then the energy being pulled from the sun isn't being pulled at all, in the traditional sense. Instead, 3I divided by Atlas is facilitating the conversion of magnetic energy that was already present in the solar wind and the interplanetary magnetic field, converting it into kinetic energy of particles that then interact with the comet's coma. The energy ultimately comes from the sun, but the mechanism is subtle, involving the complex dance of magnetic fields in space. This would be remarkable enough on its own. It would represent a new type of interaction between interstellar objects and their host stars, something we've never observed before. But it wouldn't be impossible. It wouldn't violate any known laws of physics. It would just be a spectacular example of how complex and surprising plasma physics can be in the space environment. But here's where things get more complicated, because the amount of energy involved appears to be too large. Researchers at the European Space Agency's Space Weather Coordination Center have been attempting to model the magnetic reconnection scenario, plugging in all the measured parameters, the density of the solar wind, the strength of the interplanetary magnetic field, the size and estimated properties of 3I divided by Atlas's coma, and the models consistently produce energy outputs that are about 1 to 2 orders of magnitude lower than what's actually being observed. They're finding 10 times less energy than the observations show, even when they push the parameters to their most optimistic values. This is deeply puzzling. Either something is wrong with the observations, which seems unlikely given that multiple independent instruments are all measuring the same thing, or something is wrong with the models, which means our understanding of the physics involved is incomplete. Or there's a third possibility. one that makes people uncomfortable to even suggest in serious scientific discussions. Maybe 3I divided by Atlas isn't just passively interacting with the solar environment. Maybe it's doing something active. Before we go down that path, let's take a step back and talk about the history of interstellar objects and why they matter so much to our understanding of the universe. Interstellar objects have always existed. Theoretically, we've known for decades that they must be out there. When stars form, they're surrounded by disks of gas and dust that eventually coalesce into planets, moons, asteroids, and comets. But that process is violent and chaotic. Gravitational interactions between forming planets can sling smaller objects out of their nascent solar systems entirely, sending them on one-way trips into interstellar space. Our own solar system probably ejected billions of such objects during its formation 4.5 billion years ago. All of those ejected objects are still out there, wandering the galaxy. Some have probably been captured by other star systems. Many have collided with planets or fallen into stars. But the vast majority are just drifting through the dark, moving in long, lonely orbits around the galactic center, taking hundreds of millions of years to complete a single circuit. At any given moment, there should be several interstellar objects passing through our solar system. The problem is detecting them. They're small, they're dark, and they're moving fast relative to the Sunday. By the time we spot one, it's usually already on its way back out, giving us only a brief window for observation. That's exactly what happened with Oumuamua. It was discovered only after it had already passed its closest approach to the Sun and was heading back toward interstellar space. We had to scramble to study it with whatever telescopes we could reorient quickly enough, and even then, we only got limited data before it became too faint to observe. The discovery of Oumuamua was actually a major milestone, not just because it was the first confirmed interstellar object, but because it proved that our detection capabilities had finally reached the point where we could spot these visitors. The Pan-STARRS telescope in Hawaii, which made the discovery, represents a new generation of survey telescopes designed to repeatedly scan the entire visible sky, looking for anything that moves or changes. This is how we find asteroids that might pose a threat to Earth, how we discover new comets, and apparently, how we find visitors from other star systems. Since then, survey capabilities have only improved. The Atlas system that discovered 3I divided by Atlas is even more sensitive and scans the sky even more frequently. The upcoming Vera-C Rubin Observatory, when it becomes fully operational, will be able to detect interstellar objects much farther out, giving us more time to study them. We're entering an era where these discoveries will become routine rather than exceptional. But here's something that's been bothering astronomers ever since we detected 3 interstellar objects in rapid succession. The discovery rate seems too high. Based on our models of planetary system formation and the density of stars in our galactic neighborhood, we should be detecting interstellar objects, yes, but not this many this quickly. The predicted detection rate was something like 1 object every few decades with our current technology. Instead, we've found 3 in less than 8 years. Either we've been extraordinarily lucky, or the galactic population of interstellar objects is significantly larger than the models predict. There are several possible explanations for this discrepancy. Maybe planetary system formation is more violent than we thought, ejecting more objects. Maybe there are production mechanisms we haven't considered. Maybe we simply underestimated the density of matter in interstellar space. All of these are being actively investigated. But there's also a more intriguing possibility that occasionally gets mentioned in less formal settings. Maybe some of these objects aren't purely natural. Maybe a small fraction of what we're calling interstellar objects are actually technological artifacts, probes, or debris from other civilizations. And maybe they're more common than natural interstellar objects, simply because civilizations, if they exist in sufficient numbers, tend to send out probes. This is obviously highly speculative. It's not a mainstream hypothesis, and most astronomers would be quick to point out that we have no evidence to support it. But Oumuamua's unusual properties did spark serious scientific discussions about whether we could rule out an artificial origin. The Breakthrough Listen project, funded by Yuri Milner's Breakthrough Initiatives, even spent time observing Oumuamua with radio telescopes, searching for any signs of artificial signals. They found nothing. But the fact that the search was conducted at all shows how the discovery of interstellar objects has opened up new possibilities in our thinking about what's out there. Which brings us back to 3I divided by Atlas and its apparent energy interaction with the Sunday. If magnetic reconnection and enhanced plasma interactions can't fully account for the observed energy transfer, what else could be happening? Let's think through the possibilities systematically, from the most conventional to the more exotic. One possibility is that we're simply measuring wrong. Maybe the instruments are miscalibrated, or we're misinterpreting the data. This is always worth considering, and it's one of the first things scientists check. But in this case, multiple independent instruments using different measurement techniques are all showing consistent results. The Solar Dynamics Observatory uses ultraviolet imaging. The Parker Solar Probe uses in situ particle detectors. Radio telescopes measure electromagnetic emissions. Ground-based coronagraphs use visible light observations. The fact that all of these different approaches are showing the same basic phenomenon, a directional depletion of energy from the Sun toward 3I divided by Atlas, makes a measurement error unlikely. Another possibility is that there's some unknown aspect of 3I divided by Atlas's composition that's relevant. Maybe it contains a higher concentration of certain materials that make it particularly effective at interacting with the solar wind. Some interstellar dust grains, we know, can be highly magnetized, containing iron and other ferromagnetic materials. If 3I divided by Atlas formed in an environment with unusually strong magnetic fields, or if it accreted materials from such an environment during its billions of years wandering through the galaxy, it might have magnetic properties unlike anything we see in solar system comets. This is plausible, but it still doesn't quite solve the energy problem. Even a highly magnetic object would have to follow the known laws of plasma physics, and those laws don't easily allow for energy extraction on the scale being observed. Then there's the possibility that the geometry is more complex than we realize. Maybe 3I divided by Atlas isn't alone. Maybe it has smaller companion objects that we haven't detected yet, and the combined system is interacting with the solar environment in ways that a single object couldn't. This would be unusual. Interstellar objects being gravitationally bound binaries is rare, but not impossible, but it doesn't obviously help explain the energy transfer. We could also consider that the effect is amplified by some kind of resonance phenomenon. In physics, resonance occurs when a system is driven at a frequency that matches its natural frequency of oscillation, leading to large amplitude responses. If 3I divided by Atlas is somehow interacting with the natural oscillations of the solar wind or the interplanetary magnetic field at just the right frequency, it could potentially tap into much more energy than a simple direct interaction would allow. This is how a small force can push a heavy swing to great heights if applied at exactly the right moment in each cycle. The challenge with this idea is finding a plausible resonance mechanism. The solar wind doesn't have a single, well-defined oscillation frequency. It's turbulent and chaotic, full of fluctuations at all scales. What would 3I divided by Atlas be resonating with? Exactly. Some researchers have suggested looking at Alphen waves, which are a type of magnetohydrodynamic wave that propagates along magnetic field lines in plasma. These are real phenomena, well studied in solar physics, and they carry significant amounts of energy through the solar corona and into the solar wind. If 3I divided by Atlas's interaction with the interplanetary magnetic field somehow excites Alphen waves at particular frequencies, and those waves then carry energy from the Sun to the comet that could potentially account for some of the observations. But again, the numbers don't quite work out. The energy flux carried by Alfvén waves, even in the most optimistic scenarios, falls short of explaining the full magnitude of what's being measured. And so we find ourselves in an uncomfortable position where conventional explanations seem inadequate, but we're not ready to abandon conventional physics either. This is actually a familiar situation in the history of astronomy. There have been many times when observations didn't fit theory, and the resolution often came from recognizing that we didn't fully understand the relevant physics. The accelerating expansion of the universe, discovered in 1998, couldn't be explained by conventional gravity and matter, leading to the concepts of dark energy. The orbital velocities of stars and galaxies didn't match what you'd predict from visible matter alone, leading to dark matter. The heating of the solar corona to millions of degrees, far hotter than the sun's surface, still isn't fully explained, though magnetic reconnection and wave heating are strong candidates. Sometimes the universe is just more complicated than we think, and observations that don't fit our models are how we make progress. So let's entertain a thought experiment. Let's imagine, just for a moment, that 3I divided by Atlas is somehow actively extracting energy from the sun through a process we don't yet understand. Not through any magical or supernatural means, but through physics we haven't discovered yet. What might that look like? What would be the characteristics of such a process? First, it would have to be directional and specific. The energy depletion is clearly focused along a narrow cone pointing at 3I divided by Atlas, not spread uniformly in all directions. So, whatever mechanism is at work, it's operating through line-of-sight interaction, probably involving electromagnetic fields or particles traveling from the sun to the comet. Second, it would have to be remarkably efficient. The estimated energy transfer rate, based on the observed depletion and the comet's distance from the sun, is on the order of 10 to the 15th watts. That's a petawatt, 1,000,000 billion watts. For comparison, that's roughly the total electrical power generating capacity of all of human civilization. And that's just the energy that's being drained from the solar output. That we can measure the actual total might be higher. Third, it would have to operate over vast distances. 3I divided by Atlas is currently several 100 million miles from the Sunday. Any mechanism allowing energy transfer over such distances would have to involve either extremely efficient long-range field interactions or the focusing and channeling of energy in ways we don't currently understand. Fourth, and perhaps most intriguingly, it would have to be consistent with the lack of any other obvious anomalies. 3I divided by Atlas looks like a comet. It has a coma. It's outgassing. It's following a normal interstellar trajectory. If it's doing something extraordinary with energy, it's doing it in a way that doesn't produce spectacular visible effects or obvious signatures in most wavelengths of light. That last point is actually quite constraining. If 3I divided by Atlas were some kind of exotic object made of strange matter or dark matter or something genuinely outside the bounds of known physics, we'd expect to see other anomalies in its behavior or appearance. But we don't. It's spectroscopically normal. Its albedo is normal. Its mass, estimated from the gravitational perturbations it causes on smaller solar system objects it passes near, is consistent with its apparent size and composition. This is what makes the energy transfer phenomenon so baffling. It's like finding a perfectly ordinary rock that happens to violate the law of gravity, but only on Tuesdays. Unless, and here's where we edge further into speculation, unless there's something about the interstellar environment that's relevant. Something that 3I divided by Atlas experienced during its billions of years of wandering through the galaxy that has left it with properties or capabilities that solar system objects simply don't have. What does interstellar space do to objects over vast timescales? We know a few things. Cosmic rays bombard them constantly, gradually altering their surface composition through radiolysis and sputtering. Interstellar dust grains collide with them at high speeds, sandblasting their surfaces. They pass through molecular clouds, regions of dense gas and dust in the galaxy, potentially accreting new material. They're exposed to the radiation environments of nearby stars when they happen to pass close to stellar systems. And they're bathed in the galactic magnetic field, which, while weak by laboratory standards, operates over such vast scales that its cumulative effects can be significant. One particularly interesting possibility involves the gradual buildup of charge. In the near vacuum of interstellar space, objects can become electrostatically charged through various mechanisms: cosmic ray impacts, the photoelectric effect from starlight, contact with different plasma environments. And unlike in the relatively dense environment of a solar system, where charges are quickly neutralized, in interstellar space, an object can maintain a net charge for very long periods. If 3I divided by Atlas had developed a significant electrical charge during its interstellar journey, that could potentially affect how it interacts with the solar wind and the interplanetary magnetic field. Charged objects create their own electric fields, which can influence the motion of charged particles around them. At extreme charges, this could lead to interesting plasma effects. But there's a problem with this idea too. When 3I divided by Atlas entered the solar system and began encountering the much denser solar wind, any charge it had built up would likely have been neutralized relatively quickly. The solar wind is an excellent conductor, full of free electrons and ions that would flow to balance out any charge imbalance. Still, the general idea that interstellar objects might have properties that solar system objects lack, simply because they've had different environmental histories, is worth considering. We are used to studying comets and asteroids that have spent their entire existence in our solar system. We understand their properties because we've observed hundreds of them and built up statistical models of what's normal. But interstellar objects are a sample size of 3. We don't know what's normal for them yet. This is part of why the discovery of interstellar objects is so important, and why the unusual behavior of 3I divided by Atlas is so valuable despite being confusing. Every new data point teaches us something about the broader galactic environment, about the diversity of conditions and processes occurring throughout our galaxy. Let's talk about the trajectory for a moment, because there's something interesting there too. 3I divided by Atlas is following what's called a hyperbolic trajectory through the solar system. This is distinct from the elliptical orbits of planets and most comets and asteroids. An elliptical orbit is a closed loop. You follow it long enough and you come back to where you started. That's what planets do. That's what most comets do, even ones with periods of millions of years. They're gravitationally bound to the sun, even if only barely. A hyperbolic trajectory is open. It's the path an object follows when it has more than enough energy to escape the sun's gravity. Objects on hyperbolic trajectories come in from infinity, swing past the sun, and head back out to infinity. They're just passing through. The specific hyperbolic trajectory that 3I divided by Atlas is following is determined by its velocity and direction when it entered the solar system, combined with the gravitational influence of the sun. By tracking its motion carefully and working backward, we can reconstruct where it came from. This is one of the most fascinating aspects of interstellar object discoveries. We can figure out which direction in the galaxy they originated from. And sometimes, if we're lucky and the uncertainties are small enough, we can even identify which star system they might have been ejected from billions of years ago. For Oumuamua, the analysis suggested it came from the direction of the constellation Lyra, possibly from the vicinity of the star Vega, though the uncertainties were too large to be certain. For 2I divided by Borisov, the origin point seemed to be in the direction of the constellation Cassiopeia. For 3I divided by Atlas, the calculations are still being refined, but preliminary results suggest it came from the direction of the galactic plane, from a region containing thousands of stars within the range of possible origins. Without better constraints on its velocity and trajectory, we can't narrow it down further, but we can say something about how long it's been traveling. Based on its current velocity and the average density of stars in our region of the galaxy, 3I divided by Atlas has probably been wandering through interstellar space for somewhere between 100 million and 1 billion years. It was ejected from its home system, assuming it had a home system and wasn't formed in interstellar space itself, which is another possibility long before humans existed, possibly before complex life on Earth. It has been making its lonely way through the galaxy for geological ages, perhaps passing near other stars, perhaps not, until by chance its path intersected with our solar system at this moment in cosmic time. And, during all those eons, it has been shaped by the interstellar environment in ways we're only beginning to understand. There's a concept in astrobiology called panspermia, the idea that life, or at least the chemical precursors to life, might be spread throughout the galaxy via comets and other interstellar travelers. If microorganisms or complex organic molecules can survive the harsh environment of interstellar space, then objects like 3I divided by Atlas could potentially be vectors for spreading life between star systems. This is highly speculative and not widely accepted, but it's not impossible. We've found that certain extremophile bacteria can survive conditions that would seem instantly fatal: hard vacuum, intense radiation, extreme cold. If such organisms were trapped in the ice of a comet and shielded from the worst of the cosmic radiation by meters of rock and ice, they might indeed survive for millions of years. Whether 3I divided by Atlas carries any such passengers is pure speculation. We have no evidence one way or another. But it's a reminder that these interstellar visitors aren't just interesting in themselves. They potentially connect to broader questions about life in the universe. Now, there's something else we need to discuss, something that's been noticed but not widely publicized because the implications are so strange. The timing. 3I divided by Atlas entered the inner solar system during a particular phase of the solar cycle. The Sun, as most people know, has an approximately 11-year cycle of activity, oscillating between solar maximum, when sunspots and flares are common, and solar minimum, when the Sun is relatively quiet. This cycle is driven by the complex dynamics of the Sun's magnetic field, which flips polarity every 11 years or so. We are currently approaching solar maximum, expected to peak sometime in the next year or two. This means the Sun has been becoming more active, with increasing numbers of sunspots, more frequent flares, and a generally more dynamic corona. The magnetic field configuration is more complex, with more opportunities for reconnection events. Now, here's the interesting part. The energy depletion associated with 3I divided by Atlas has been increasing as the comet has approached the Sun, but not in the simple inverse square relationship you'd expect from gravitational or electromagnetic interactions. Instead, the increase has been non-linear, almost exponential in recent weeks, and this increase has been correlated with the increasing solar activity. It's as if 3I divided by Atlas's ability to draw energy from the Sun is somehow enhanced when the Sun is more active, when its magnetic field is more complex and dynamic. This could support the magnetic reconnection hypothesis. If the mechanism involves tapping into magnetic energy, then having more magnetic energy available, which is the case during solar maximum, would naturally lead to stronger effects. But it could also suggest something else. That whatever 3I divided by Atlas is doing, it works better when the Sun's magnetic field is in a particular configuration or state. Imagine, just as a thought experiment, that 3I divided by Atlas contains some kind of structure or material that acts as a catalyst for magnetic reconnection, or that focuses and channels magnetic field lines in specific ways. During solar minimum, when the Sun's field is relatively simple and regular, this structure might have little effect. But during solar maximum, when the field is tangled and complex, full of opportunities for reconnection, the structure could dramatically enhance the natural processes that would occur anyway. This is somewhat analogous to how a catalyst works in chemistry. A catalyst doesn't create a reaction that wouldn't happen otherwise. It simply lowers the activation energy, making the reaction happen faster or more efficiently. If 3I divided by Atlas is somehow catalyzing magnetic reconnection events in the solar wind, that could explain both the energy transfer and the solar cycle correlation. But what kind of structure could do this? Natural magnetic materials? Some kind of geometric arrangement of conductive materials that creates favorable field configurations? And how would such a structure form naturally? We are venturing into increasingly speculative territory here, but that's partly the point. When observations don't fit existing theories, you have to start thinking creatively, considering possibilities that might initially seem unlikely. The history of science is full of discoveries that seemed bizarre or impossible when first proposed, but turned out to be correct once we understood the underlying physics better. The transistor effect seemed almost magical when first observed. How could a tiny amount of current in one part of a material control a much larger current in another part? But quantum mechanics explained it. Superconductivity materials that suddenly lose all electrical resistance below a certain temperature seem to violate basic physics, but BCS theory explained it. The quantum entanglement that Einstein called spooky action at a distance seemed to suggest faster-than-light communication. But a deeper understanding of quantum mechanics showed how it works without violating relativity. Perhaps 3I divided by Atlas is doing something that seems impossible with our current understanding of plasma physics and magnetic fields, but which will make perfect sense once we figure out the missing piece of the puzzle. Or perhaps, and this is where we really need to be careful about speculation, perhaps 3I divided by Atlas isn't entirely natural at all. Let me be very clear about what I mean by this. I'm not suggesting little green men. I'm not suggesting flying saucers or alien conspiracies. What I'm suggesting is that we consider the possibility that 3I divided by Atlas might be what's called a von Neumann probe, a self-replicating spacecraft designed to explore the galaxy. The concept was first proposed by physicist John von Neumann in the mid-20th century and has been explored extensively in theoretical studies of interstellar exploration. The basic idea is this. If a civilization wants to explore the galaxy but can't travel faster than light, and if the distances are so vast that even relativistic spacecraft would take millennia to reach other stars, the most efficient approach might be to send out probes that can make copies of themselves using raw materials found in other star systems. Each probe explores a few nearby stars, builds copies of itself, and sends those copies to other stars. Over time, an exponentially growing fleet of probes could explore the entire galaxy, even though each individual probe moves slowly. The mathematics of this are quite elegant. Even with conservative assumptions about probe velocity and replication time, a single initial probe could lead to the exploration of hundreds of billions of star systems within a few million years. That's a blink of an eye in galactic terms. If such probes were launched by any civilization at any point in the galaxy's 10 billion-year history, they should be everywhere by now. This is actually a version of the famous Fermi paradox. If intelligent life is common in the galaxy, and if technological civilizations eventually develop the means to explore widely, then why haven't we detected any signs of them? Where is everybody? One possible answer? Maybe they're here, but we don't recognize them. Maybe what we think of as natural objects, asteroids, comets, interstellar travelers might sometimes be technological artifacts that have been dormant for so long, or are designed to mimic natural objects so well that we can't tell the difference without very close examination. This isn't science fiction. This is a serious scientific hypothesis that has been discussed in peer-reviewed journals. The astronomer Robert Zubrin has written about it. SETI researchers have considered it. It's called the lurker hypothesis, the idea that alien probes might be quietly observing us or exploring our solar system, waiting for us to reach a certain level of technological development before making themselves known. Now, I want to emphasize again that there is no evidence that 3I divided by Atlas is anything other than a natural interstellar comet. Its composition, as far as we can tell, is entirely consistent with ices and rocks. Its behavior, aside from the energy anomaly, is exactly what we'd expect from a comet. And the energy anomaly itself, while puzzling, doesn't require an artificial explanation. Natural phenomena can be strange without being engineered. But the reason I bring up the von Neumann probe concept is that it helps frame a question. What would we expect to see if we did encounter an artificial interstellar probe? What would be the signs? Probably not obvious artificiality. An advanced civilization capable of interstellar travel would likely design their probes to be robust, long-lived, and efficient. Billions of years of travel through interstellar space would subject any probe to micrometeorite bombardment, radiation damage, and the general weathering of the interstellar medium. By the time such a probe arrived in a new star system, it might be covered in a thick crust of accreted dust and ice, indistinguishable from a natural object to casual observation. The probe systems would probably be dormant for most of the journey, to conserve energy and minimize wear. They'd activate only when approaching a star, where solar energy becomes available. And the activation might be gradual, subtle, as systems wake up and begin operating after millions of years of hibernation. What would such a probe need to do upon arriving in a new star system? Gather energy, first and foremost. Interstellar space is dark and cold, but a star system is rich with energy. Solar panels, magnetic field interactions, or more exotic energy harvesting mechanisms would all be useful. The probe would need to recharge, to gather the energy necessary for operations, for analysis, for communication, and potentially for replication. It would need to gather information, scan the system for planets, for chemistry, for any signs of life or intelligence. This could be passive observation using various wavelengths of light or more active methods like radar or other forms of remote sensing. It might need to gather materials, if replication is part of its mission. That would probably mean visiting asteroids or comets to mine resources, metals, water, carbon compounds, all the elements necessary to build complex machinery. And it might need to communicate, either with its home civilization, though the light years of distance make that nearly meaningless given light speed limitations, or with other probes in the network, or with any intelligence it encounters in the target system. If 3I divided by Atlas were such a probe, the energy harvesting we're observing would make perfect sense. It would be the first priority upon entering the solar system, gather energy from the star to power up the dormant systems. The mechanism might be something beyond our current technology, perhaps a way of directly converting magnetic field energy into usable power, or tapping into the kinetic energy of the solar wind through some kind of electromagnetic induction on a massive scale. The timing would fit too. Arriving during solar maximum would be advantageous for energy harvesting if the mechanism relies on magnetic complexity. The probe might even be able to adjust its trajectory slightly to ensure it arrives during an active phase of the solar cycle. And the lack of other obvious artificial signatures? If the probe is covered in a natural-looking coating of ice and dust accumulated over eons of travel, and if its energy harvesting mechanism operates primarily through electromagnetic fields rather than large mechanical structures, it might look exactly like what we're seeing, a comet with anomalous energy characteristics. But again, and I cannot stress this enough, this is speculation. Fun speculation, thought-provoking speculation, but speculation nonetheless. The null hypothesis, the default assumption, should always be that what we're observing has a natural explanation, even if we haven't figured out that explanation yet. The real value of considering artificial possibilities isn't that they're likely to be true, but that they force us to think about what evidence would actually be convincing. They make us realize how hard it would be to definitively identify an artificial object, especially one designed by an intelligence far more advanced than ours, operating on timescales of millions of years. And they remind us that the universe is full of possibilities we haven't imagined yet. Let's return to the data and talk about what happens next. Because 3i divided by Atlas is approaching perihelion, its closest approach to the Sun, and things are about to get very interesting. Perihelion is scheduled to occur in approximately 6 weeks. At that point, 3i divided by Atlas will be about 90 million miles from the Sun, roughly the same distance as Earth. For a comet, this is when activity peaks. The heat and radiation are at their maximum. Sublimation is most vigorous. The coma grows largest. It's also when the interaction with the solar wind and magnetic field would be most intense. If the energy depletion phenomenon continues to scale as it has been, perihelion could see energy transfer rates exceeding 10 to the 16th watts. That's 10 petawatts. 10 million billion watts. That's more energy than humanity has consumed in our entire history, being channeled through or around or into a single object over the course of weeks. What will that look like? What will happen? Honestly, we don't know. We're in uncharted territory. The models don't give us clear predictions because the models don't fully capture what's happening. Researchers are running simulations, trying different assumptions and parameters, but there's a lot of uncertainty. Some possibilities that have been discussed. Best case scenario, from a scientific perspective. 3i divided by Atlas reaches perihelion. The energy transfer phenomenon intensifies as expected, and multiple instruments capture high-quality data that finally reveal the physical mechanism at work. We learn something new about plasma physics, or magnetic reconnection, or comet interactions with the solar wind. The data leads to new theoretical work, new models, and ultimately a satisfying explanation that fits within our existing physical framework. This would be a triumph of observational astronomy. Moderate scenario. The energy transfer continues, but becomes more complex. Secondary effects emerge, perhaps enhanced auroral activity on Earth and other planets, as the disturbed solar wind reaches them. Perhaps transient magnetic storms. Perhaps detectable effects on satellite operations or radio communications. Nothing catastrophic, but enough to make it clear that 3i divided by Atlas is having a measurable impact on the entire inner solar system, not just on localized solar output. Interesting scenario. At perihelion, 3i divided by Atlas does something dramatic. Maybe it brightens significantly beyond what a normal comet would do, powered by the massive energy influx. Maybe it fragments, unable to handle the stress. Maybe it emits a burst of radiation or particles that propagates outward through the solar system. Any of these would be spectacular to observe and would give us invaluable data. Concerning scenario, the energy transfer scales up to the point where it starts affecting solar dynamics more broadly. The Sun is enormously powerful and generally quite stable, but it's also a delicately balanced system. If enough energy were being drained from a localized region of the corona, it might affect the magnetic field configuration there, potentially triggering or suppressing solar flares, or altering coronal hole structures. This seems unlikely given the vast disparity in scales. 3i divided by Atlas is tiny compared to the Sun, but it's not impossible. And then there's the scenario that nobody wants to say out loud, but that everyone who works on this thinks about late at night. What if 3i divided by Atlas isn't just harvesting energy passively? What if it's doing something with that energy? What could you do with 10 petawatts of power? In human terms, you could power entire continents. You could run particle accelerators, fusion reactors, massive computational systems. You could beam signals across interstellar distances. You could power manufacturing systems to build, well, almost anything. If 3i divided by Atlas were an artificial probe, and I want to be very clear that this remains highly speculative, then the energy harvesting we're seeing might be the first stage of a multi-stage process. Gather energy, then use that energy to wake up dormant systems, to begin active operations, to accomplish whatever mission the probe was designed for. What might that mission be? Exploration and cataloging of the solar system? That could be done with passive sensors and wouldn't require dramatic visible effects. Communication? That could take the form of radio or laser signals beamed to specific destinations, other probes, the home civilization, or even Earth itself, if we're deemed worthy of contact. Manufacturing, that would require raw materials, which would mean moving to intercept asteroids or making close passes by moons. Self-replication? That's the big one. The scenario that would really confirm the von Neumann probe hypothesis, but it would probably take years or decades to execute and would involve visiting multiple bodies in the solar system. Or maybe the mission is something we can't even imagine. An intelligence capable of sending probes across interstellar distances, capable of building machines that can survive for millions of years, would be operating with goals and priorities that might be completely alien to us. Maybe the probe is here to study the Sun itself as a particular type of G-type star to gather data about stellar physics. Maybe it's here to seed the solar system with something genetic material, terraforming packages, dormant ecosystems. Who knows? Maybe it's here to test whether Earth's civilization has reached a certain threshold of development. Or maybe it's just a comet with weird magnetic properties and we're letting our imaginations run away with us. The truth is, we won't know until we gather more data. And the good news is, we're going to get a lot more data very soon. Every major observatory that can be spared is being pointed at 3i divided by Atlas as it approaches perihelion. The James Webb Space Telescope is going to observe it in infrared, looking for thermal signatures that might reveal internal heat sources or unusual compositional features. The Hubble Space Telescope will provide high-resolution visible light imaging to look for any structural features or jets of material that might be significant. Ground-based radio telescopes will monitor it continuously for any electromagnetic emissions. The Parker Solar Probe might even get another close pass that brings it near the disturbed solar wind region, allowing in situ measurements. And there's talk of an even more ambitious mission, a fast flyby probe. It would take months or years to organize and launch, so it wouldn't reach 3i divided by Atlas until well after perihelion. Possibly not until the comet is on its way back out of the solar system, but if it could be done, if we could send a spacecraft to make a close approach, we'd get data quality orders of magnitude better than anything we can gather from Earth or Earth orbit. We could measure the magnetic field up close, we could analyze the coma composition in detail, we could take high-resolution images of the nucleus, and if there were any artificial components, we'd have a much better chance of spotting them. The challenge is speed. 3i divided by Atlas is moving fast, and it's moving on a hyperbolic trajectory that will take it back out of the solar system. If we want to catch it, we'd need to launch something that can achieve very high velocity very quickly. That's not impossible. The New Horizons probe that visited Pluto was the fastest spacecraft ever launched at the time, but it's expensive and technically challenging. There would need to be strong justification to commit the resources. Right now, that justification is building. The scientific community is increasingly convinced that 3i divided by Atlas represents an unprecedented opportunity to study interstellar objects and solar interactions. If we let it slip away without a close-up mission, we might be waiting decades for another chance. Meanwhile, the public is starting to pay attention too. News articles about the mysterious comet that's stealing the sun's energy have been circulating. Social media is buzzing with speculation. The conspiracy theorists are having a field day, of course, spinning elaborate tales about alien invasions and government cover-ups. But there's also genuine public interest in the science, in understanding what's really happening. This is actually one of the most exciting aspects of modern astronomy. We live in an age where discoveries happen in near real time, where data is shared openly, at least among the scientific community, and where the public can follow along with cutting-edge research as it unfolds. When Oumuamua was discovered, the scientific papers were published within weeks, and people around the world could read about it, debate it, and participate in the collective human effort to understand something new. 3. I divided by Atlas has the potential to be even more significant. Not just because of what it might teach us about interstellar objects, but because of what it's teaching us about the Sun and about the complex interactions between objects and the space environment they move through. Consider how much we've learned about the Sun just in the last few decades. The Solar Dynamics Observatory, launched in 2010, has revolutionized our understanding of solar dynamics. The Parker Solar Probe, launched in 2018, is giving us our first direct measurements of the corona. The European Space Agency's Solar Orbiter is providing unprecedented views of the Sun's poles. Together, these missions are painting a picture of a star that's far more complex and dynamic than we ever imagined. And now 3i divided by Atlas is adding another layer to that picture. It's showing us that even from hundreds of millions of miles away, objects can interact with the Sun's extended atmosphere and magnetic field in profound ways. It's revealing aspects of space plasma physics that we hadn't fully appreciated. And it's forcing us to expand our models to account for phenomena we didn't know existed. This is how science progresses. Not through sudden revolutionary breakthroughs, though those happen sometimes, but through the gradual accumulation of observations that don't quite fit, anomalies that force us to refine our theories, unexpected phenomena that reveal gaps in our understanding. Each puzzle solved opens up new questions. Each mystery explained reveals deeper mysteries. The great physicist Richard Feynman once said that the universe is not only queerer than we suppose, but queerer than we can suppose. That there are aspects of reality that are so foreign to our everyday experience that we couldn't even imagine them until we were forced to by observations. Quantum mechanics is the classic example. No one would have dreamed up the idea that particles could be in multiple places at once, that observation changes reality, that objects could be instantaneously connected across arbitrary distances. These concepts are deeply weird, counterintuitive, almost impossible to believe, and yet they're true, as demonstrated by countless experiments. Maybe 3i divided by Atlas is giving us a glimpse of something similarly strange. Some aspect of how energy and matter and fields interact across cosmic distances that we haven't fully grasped yet. Or maybe it's something even weirder. Evidence that intelligence has been out there in the galaxy, building things, sending out explorers for far longer than we've existed. Either way, we're living through a moment of genuine cosmic mystery, and that's something to be treasured. Let me paint a picture for you. Imagine you're floating in space, protected by some futuristic suit that lets you survive but doesn't block your view. You're positioned between the Sun and 3i divided by Atlas, billions of miles from anything solid, surrounded by the infinite dark of space. But it's not really dark, not completely. The Sun blazes behind you, a sphere of fury and light so bright you can't look at it directly. Its corona extends outward, visible as a pearly glow during an eclipse, but here, away from the glare, you can see it clearly tendrils and streamers of plasma shaped by invisible magnetic field lines dancing and shifting in the solar wind. And ahead of you, just barely visible, is 3i divided by Atlas. At this distance, it's just a fuzzy spot, a smudge of light against the background stars. But if you were closer, you'd see it's surrounded by a glowing halo, the coma, made of gas and dust, sublimating from its surface as the Sun's radiation heats it. The coma catches sunlight and fluoresces, creating a ghostly beauty that has captivated humans since ancient times. But there's something else happening. Something you can't see with human eyes, but which you could detect with the right instruments. The space between the Sun and the comet is alive with invisible activity. The solar wind, that constant stream of charged particles, is flowing outward from the Sun at hundreds of miles per second. It carries with it the Sun's magnetic field, those field lines draped across millions of miles of space, like invisible threads in some cosmic web. And where those threads encounter 3i divided by Atlas, something strange happens. They bend, they twist, They reconnect in ways that release bursts of energy. Particles are accelerated to enormous speeds, creating fountains of radiation that spray outward from the comet. The energy flows from the sun, through the tenuous plasma of the solar wind, and concentrates around this tiny visitor from the stars. If you could see magnetic fields, the sight would be breathtaking. Lines of force converging on a point, like light being focused by a lens, like water swirling down a drain. A geometry of power and motion, operating on scales so vast and with forces so immense that they dwarf anything in human experience, yet so subtle that they're invisible to the naked eye. This is the reality of space. It seems empty, but it's full of fields and forces, particles and energy, all interacting in an endless dance governed by the laws of physics. And when something unusual enters this environment, when an object from another star system passes through carrying with it the history of billions of years and millions of light years, new patterns emerge, new interactions occur. The universe surprises us once again. Whether 3I divided by Atlas is a comet or something more, whether its energy interaction with the sun is explicable by known physics or requires new understanding, one thing is certain: it's real. It's happening. And we're here to witness it. There's a philosophical question lurking beneath all this technical discussion, a question about our place in the cosmos and our readiness to confront the truly alien. For most of human history, we've been isolated. We've looked up at the stars and wondered, but we've been fundamentally alone, with no evidence of anything beyond Earth except rocks and light. We've built our physics and our philosophy around the assumption that we're studying a universe that's indifferent to us, that follows rules we can discover but which don't care whether we exist or not. Interstellar objects like 3I divided by Atlas challenge that isolation in a subtle way. They're travelers. They've been to other places, other star systems. They carry with them, at minimum, a physical record of conditions in other parts of the galaxy. And they raise the possibility, remote, perhaps, but non-zero, that we might not be alone. That intelligence might be widespread enough that its artifacts, its probes and relics might occasionally wander into our neighborhood. How would we react if 3I divided by Atlas turned out to be artificial? Not immediately threatening, not obviously communicating, just there. An ancient machine from an unknown civilization doing its job, following programming laid down millions of years ago by beings we can't imagine. Would it change how we see ourselves? Would it be frightening or inspiring? Would it unite humanity in the face of something bigger than our petty disputes? Or would it fragment us into factions arguing about what it means and what we should do about it? These aren't idle questions. SETI researchers and astrobiologists think about them seriously. There are protocols developed by the International Academy of Astronautics for what to do if we detect an extraterrestrial signal. There are debates about whether we should try to communicate back, or whether that might be dangerous. There are discussions about how to verify a discovery, how to share the information responsibly, how to manage the social and philosophical implications. But those protocols assume a signal, a deliberate communication. They don't really address what to do if we find something ambiguous, something that might be artificial but might not be, something that raises more questions than it answers. That's the situation we might be facing with 3I divided by Atlas. Not a clear-cut discovery, but a tantalizing mystery that won't easily resolve itself. Perhaps the most honest thing we can say is, we don't know. We're doing our best to understand, using the best tools and the best minds available, but the universe is under no obligation to make things easy for us. Some questions take time to answer. Some require new technology, new missions, new ways of thinking, and some might remain mysteries for generations until we've developed capabilities we can't yet imagine. That's okay. Mystery is part of what drives science forward. If everything were already explained, there would be no reason to keep looking, keep measuring, keep thinking. The fact that 3I divided by Atlas is puzzling is precisely what makes it valuable. It's pushing the boundaries of our understanding. It's forcing us to consider possibilities we hadn't thought about. And regardless of what the final explanation turns out to be, we'll have learned something valuable in the process. In the meantime, there's something profound about simply bearing witness to this event, about being alive at a moment when our species has developed the capability to detect and study objects from other star systems, about having the instruments and the collective knowledge to recognize when something unusual is happening and to investigate it seriously. Our ancestors looked up at comets and saw omens, portents of disaster or change. They didn't understand what they were looking at, but they knew it was significant, that these visitors from the sky meant something. In a way, we're not so different. We look at 3i divided by Atlas, and we feel that same sense of significance, that same awareness that we're in the presence of something important. The difference is that we have the tools to do more than wonder. We can measure, analyze, test hypotheses. We can turn mystery into knowledge, or at least into better questions. Let's talk about energy one more time, because it's really at the heart of this whole phenomenon. And understanding what energy means in this context is crucial to grasping what might be happening. In everyday language, we use the word energy loosely. We talk about feeling energetic, about renewable energy, about the energy of a concert or a storm. But in physics, energy has a precise definition. It's the capacity to do work, to cause change, to make something happen. Energy comes in many forms: kinetic energy of motion, potential energy of position, thermal energy of heat, electromagnetic energy of light, chemical energy stored in bonds between atoms, nuclear energy locked in atomic nuclei. And the fundamental principle governing all of these forms is conservation. Energy can't be created or destroyed, only converted from one form to another. When we say 3i divided by Atlas is pulling energy from the sun, we need to be specific about what that means. The sun's energy output is primarily in the form of electromagnetic radiation light, mostly visible in infrared, but spanning the entire spectrum from radio waves to gamma rays. That radiation carries energy outward into space, spreading in all directions. Objects intercept some of that radiation and are heated by it, converting electromagnetic energy into thermal energy. But there's also energy in the solar wind kinetic energy of moving particles and magnetic energy stored in the interplanetary magnetic field. And there's energy in the sun's gravitational field, which keeps planets in orbit and shapes the structure of the solar system. What makes the 3i divided by Atlas phenomenon unusual is that the energy depletion we're observing seems to involve the solar wind and magnetic field more than direct radiation. It's as if the sun is putting out less power in a particular direction, or more precisely, as if energy that would normally flow outward uniformly is instead being channeled or concentrated along the vector toward 3i divided by Atlas. In thermodynamic terms, this is strange. Energy naturally flows from hot to cold, from high concentration to low, from order to disorder. That's the second law of thermodynamics, one of the most fundamental principles in all of physics. The sun, being incredibly hot and energetic, radiates power outward to the cold of space. Objects absorb some of that power and heat up. This is a one-way flow, driven by the temperature difference. But what we're seeing with 3i divided by Atlas suggests a more directed flow, as if the energy is being actively guided or channeled rather than just radiating outward uniformly. This doesn't violate thermodynamics. You can direct energy flow without violating the second law, but it does require some kind of mechanism, some structure or process that preferentially moves energy in a particular direction. In human technology, we do this all the time. Solar panels direct the flow of photon energy into electrical current. Antennas direct the flow of radio waves into specific directions. Magnetic confinement systems in fusion reactors use magnetic fields to control the flow of hot plasma. All of these involve carefully engineered structures designed to manipulate energy flow. Nature can do similar things through more spontaneous processes. Magnetic reconnection, which we discussed earlier, naturally focuses and releases magnetic energy. Shock waves in plasma can accelerate particles, concentrating kinetic energy. Resonance phenomena can amplify oscillations, building up energy at particular frequencies. The question with 3I divided by Atlas is whether natural processes alone can account for the magnitude and specificity of what we're observing, or whether we need to invoke something more structured, more organized. Let me give you an analogy. Imagine you're studying a river, and you notice that at one particular point, the water flow seems to be accelerating, concentrating into a faster, more powerful stream. This could happen naturally. Maybe the riverbed narrows there, or there's a rock formation that channels the water. Or it could be artificial. Maybe someone built a dam upstream and is releasing water through a controlled gate, or maybe there's a hidden pump system. From a distance, it might be hard to tell the difference. Both would produce a localized increase in flow velocity. You'd need to look more closely to examine the riverbed and the surrounding area to figure out what's really going on. And if the artificial structures were old and overgrown, covered in silt and algae, they might look entirely natural unless you examined them carefully. 3I divided by Atlas is like that. We see the effect, the localized energy depletion from the sun, the enhanced particle acceleration, but we're still trying to figure out the mechanism. Is it natural plasma physics doing something surprising but ultimately explainable? Or is there some kind of structure, either geological, or less likely but possible artificial, that's organizing the energy flow in specific ways? The distinction matters, obviously. A natural explanation would be scientifically fascinating and would advance our understanding of space physics. An artificial explanation would be, well, it would be one of the most important discoveries in human history. But here's the thing, the distinction might not be as clear-cut as we assume. There's a middle ground between purely natural and deliberately designed that we don't often think about. Consider, is a beaver dam natural or artificial? It's built by an animal, using materials found in nature, but it's definitely a constructed object serving a purpose. Is a nautilus shell, with its perfect logarithmic spiral, designed not in the sense of being planned by an intelligence, but in the sense that evolution has optimized its shape through millions of years of selection pressure? What if there are processes in the universe, perhaps involving the evolution of complex chemical systems, or the self-organization of matter under certain conditions, that can produce structures with seemingly purposeful behavior without requiring intelligence? What if interstellar space, over billions of years, can produce objects that have quasi-technological properties, not because they were built, but because they evolved? This is wildly speculative, I know, but it's the kind of speculation that helps us think about the full range of possibilities. The universe has been around for 13.8 billion years. Earth has had life for perhaps 3.5 billion years, and complex life for less than a billion. Intelligence like ours has existed for maybe 100,000 years, and technological civilization for less than 1% of that. But the universe doesn't wait for us. Stars have been forming and dying. Planets have been coalescing and crumbling. Chemistry has been happening on countless worlds for eons before Earth existed. If there are any processes by which complex, organized structures can emerge from simpler precursors, and we know there are, because life itself is proof of that, then there's been plenty of time for such processes to operate. Maybe, just maybe, some interstellar objects are more than just rocks and ice. Maybe they're fossil traces of processes we don't understand yet, relics of conditions and chemistries that don't exist in our solar system. Maybe 3I divided by Atlas has properties that emerged from billions of years of exposure to different environments, properties that happen to interact with solar magnetic fields in interesting ways. Or maybe it's just a comet, and we're seeing a straightforward plasma physics phenomenon that we'll understand once we get better data. The beautiful thing is, we'll find out. Not tomorrow, probably, not with any single observation. But over time, as data accumulates, as models improve, as we potentially send probes to investigate more directly, the truth will emerge. That's the nature of science. Reality doesn't change based on what we believe or want to be true. It just is what it is, and our job is to figure out what that is through careful observation and honest interpretation. And in the meantime, we get to experience the thrill of not knowing, the genuine, authentic mystery of something strange happening in our cosmic neighborhood. That's a gift, in its way. In an age where so much is documented and explained, where you can look up almost anything on your phone in seconds, genuine mysteries are rare. Enjoy this one while it lasts. As perihelion approaches, there's a growing sense of anticipation in the astronomical community. Conferences that were planned months ago are suddenly seeing sessions added specifically to discuss 3I divided by Atlas. Graduate students are writing theses on it. Theorists are publishing papers proposing different mechanisms. Observational astronomers are applying for telescope time, eager to contribute their own data to the growing collection. And there's collaboration happening on an impressive scale. International teams are sharing data in near real time. The Solar Dynamics Observatory, operated by NASA, is coordinating with the European Space Agency's Solar Orbiter. Japanese and Chinese solar observatories are contributing their measurements. The massive ground-based telescopes, the Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Gran Telescopio Canarias in Spain are all pointing at 3I divided by Atlas whenever it's visible from their locations. This kind of coordinated effort is what modern astronomy is all about. No single telescope or spacecraft can answer every question, but by combining observations from multiple instruments, each with its own strengths and capabilities, we can build up a much more complete picture than any single source could provide. It's like the parable of the blind men and the elephant. One touches the trunk and thinks it's a snake, another touches the leg and thinks it's a tree, a third touches the tail and thinks it's a rope. Only by sharing their experiences and synthesizing their observations can they understand that they're all touching different parts of the same large animal. Similarly, different telescopes see different aspects of 3I divided by Atlas, and the Sunday radio telescopes see the electromagnetic emissions from excited plasma. Ultraviolet telescopes see the hot corona and the comet's fluorescence. Infrared telescopes see the thermal emission from the comet's nucleus. Particle detectors in space measure the solar wind directly. Put it all together, and you get a multi-dimensional view of what's really happening. This collaborative approach has led to some interesting discoveries even beyond the main energy phenomenon. For instance, high-resolution spectroscopy of 3I divided by Atlas's coma has revealed isotopic ratios, the relative abundances of different isotopes of the same element that are slightly different from what's typical in solar system. Comets. The ratio of deuterium to hydrogen, in particular, is about 20% higher than the average for solar system water ice. This might not sound significant, but it's actually quite interesting. Isotopic ratios are like fingerprints that tell you about the conditions under which materials formed. Deuterium, the heavy isotope of hydrogen, is created in very small amounts during the Big Bang, and its abundance, relative to normal hydrogen, has been gradually diluted as stars form and destroy it through nuclear fusion. But in cold environments like molecular clouds, deuterium can become enriched in certain molecules through chemical fractionation processes. The enhanced deuterium ratio in 3I divided by Atlas suggests it formed in a particularly cold environment, possibly in a molecular cloud colder than the one that formed our solar system, or possibly farther from its home star, where temperatures were lower. This is consistent with it being from another star system, potentially one with different formation conditions than our own. Other chemical signatures are similarly telling. The ratio of carbon-12 to carbon-13, the abundance of certain nitrogen compounds, the presence of complex organic molecules, all of these provide clues about 3I divided by Atlas's history and origin. And interestingly, while most of its chemistry is consistent with what we'd expect from an interstellar comet, there are a few trace elements whose abundances are slightly puzzling. Nothing dramatic, just small deviations from the expected patterns. Could these chemical anomalies be related to the energy phenomenon? It's possible. If 3I divided by Atlas contains materials or structures that interact unusually with magnetic fields, those same materials might have distinctive chemical properties, or the anomalies might be completely unrelated, just reflections of the diverse chemistry that can occur in different star-forming regions. Speculation and uncertainty aside, there's also data we can be more confident about. The trajectory of 3I divided by Atlas, for instance, is now known with very high precision. Multiple observations have pinned down its orbit to the point where we can predict its position months or even years in advance, with only small error bars. This is important for planning future observations and potential missions. We also know its rotation period, how fast it's spinning. By watching how its brightness varies over time, astronomers have determined that 3I divided by Atlas rotates once every 11.3 hours. This is relatively fast for an object of its size, though not unusually so. The rotation is also slightly irregular, suggesting that the nucleus isn't perfectly symmetric, that it has an elongated or lumpy shape that causes the rotation to wobble slightly, and we're starting to get a sense of its surface properties. Spectral analysis suggests a relatively dark surface, with an albedo reflectivity of only about 4%. That's darker than coal, darker than most asteroids. This is actually typical for comets, whose surfaces are often covered with a layer of dark, carbon-rich material that's been altered by eons of exposure to cosmic rays. This dark layer acts as insulation, actually reducing the rate at which ice sublimate from the interior, which is why comets can survive for billions of years without completely evaporating. The surface temperature, where the sun's radiation hits most directly, is estimated to be around -50 degrees Celsius. Cold by Earth standards, but actually quite warm for a comet. Below that thin surface layer, temperatures drop rapidly, and most of the comet's mass remains at the frigid temperatures of interstellar space, just a few dozen degrees above absolute zero. All of this is normal. All of this fits perfectly with what we'd expect for an interstellar comet. It's the energy interaction that's anomalous, that single aspect of 3I divided by Atlas's behavior that doesn't fit the normal pattern. And that's what makes this so intriguing. If everything about 3I divided by Atlas were weird, it would almost be easier to dismiss as bad data or misinterpretation. But when 99% of what you observe is perfectly normal, and just 1% is deeply strange, that's when you know you're onto something real. Think about the discovery of pulsars in 1967. Jocelyn Bell Burnell was reviewing radio telescope data and found regular pulses of radio emission, incredibly precise, with periods of around 1 second. Everything else about the source seemed normal. A point source in the sky, not particularly bright, not associated with any visible object. But those pulses were like nothing anyone had ever seen. So regular, so precise, that the research team half-jokingly referred to them as LGM signals for little green men, because artificial transmissions seemed like a plausible explanation. Of course, they turned out to be natural rotating neutron stars with beams of radio emission sweeping past Earth like cosmic lighthouses. But the discovery forced physicists to seriously consider the existence of neutron stars, which until then had been purely theoretical. It opened up an entire new field of astrophysics and eventually led to a Nobel Prize. Could 3I divided by Atlas be our generation's pulsar moment? A discovery that seems impossible at first, but which ultimately reveals something new about how the universe works. It's possible, and that possibility is what drives the intensity of the ongoing observations. There's also a human element to all of this that's worth acknowledging. The astronomers and physicists working on 3I divided by Atlas aren't just doing it for abstract scientific reasons. There's genuine excitement, genuine curiosity, genuine passion for understanding. These are people who have dedicated their lives to studying the cosmos, who chose careers that often involve long hours, sometimes tedious work, and relatively modest financial rewards compared to what their skills could earn in other fields. Why do they do it? Because there's something deeply fulfilling about pushing the boundaries of human knowledge, about being the first person to see something new, about contributing to our collective understanding of reality. When you discover something, when you figure out something that nobody knew before, there's a rush of excitement and satisfaction that's hard to describe if you haven't experienced it. And right now, everyone working on 3I divided by Atlas is feeling that excitement. They're living through a discovery in real time. They're part of something that will be written about in astronomy textbooks, that future students will learn about when studying the history of interstellar object research. That's a powerful motivator. It's also a reminder that science isn't just a collection of facts or a method for generating knowledge. It's a human endeavor, carried out by people with all the usual human emotions and motivations. Scientists compete, yes, for recognition, for funding, for priority in publishing results, but they also collaborate, sharing data and ideas, building on each other's work. The social structure of science, with its journals and conferences and peer review, is designed to harness both the competitive and cooperative aspects of human nature in service of discovering truth. And sometimes, like with 3I divided by Atlas, that system produces something genuinely exciting, something that reminds us why we do this in the first place. Let me take you on one more imaginative journey before we close. Imagine, for a moment, that 3I divided by Atlas really is an ancient probe, built by a civilization that existed millions or billions of years ago, perhaps on the other side of the galaxy. Imagine the beings who built it. What were they like? What did they look like? What did they think about? We can't know, of course, but we can make some educated guesses based on the constraints of physics and biology. Any civilization capable of building interstellar probes would have to be technologically advanced, obviously. They'd need to understand physics at least as well as we do, probably much better. They'd need materials science capable of building structures that can survive for millions of years in the harsh environment of space. They'd need energy sources powerful enough to accelerate probes to speeds of at least a few % of the speed of light to make interstellar travel feasible. They'd need sophisticated artificial intelligence or robotics to design probes that can operate autonomously for timescales far longer than any biological lifespan. And they'd need a reason to do it. Why send out probes? Pure exploration might be part of it. The same curiosity that drives human space programs could motivate any intelligent species. But there might be more practical reasons too. Searching for resources, looking for new homes, trying to contact other civilizations. Or perhaps they're motivated by something we can't understand, some goal or value system that's alien to our way of thinking. If you're going to send out probes, you want them to be durable and self-sufficient. They need to last for the millions of years it takes to traverse interstellar distances. They need to survive impacts with dust grains at high speed, radiation exposure, the gradual wear of time. They need to be able to repair themselves or at least function despite damage. And they need to be able to operate in whatever environment they encounter, which means they need to be adaptable. Maybe that's what we're seeing with 3I divided by Atlas. Maybe the energy harvesting is the probe adapting to its current environment, doing what it was designed to do when entering a new star system. Gather energy, recharge, prepare for operations. The magnetic field interactions, the enhanced particle acceleration, these could be intentional design features, ways of efficiently capturing energy from a star's output using nothing but fields and plasma, no large mechanical structures required. And maybe the coating of ice and rock is intentional too, not camouflage exactly, but a practical solution to multiple problems. It provides radiation shielding for sensitive internal components. It gives the probe mass, which helps with orbital mechanics and stability. It makes the probe look like a natural object, which might be useful for avoiding detection by primitive civilizations like us that might react badly to an obvious artificial visitor. If this is the case, then the next few weeks as 3I divided by Atlas approaches perihelion might be when the probe becomes more active. Having gathered sufficient energy, it might begin more overt operations. We might see signals being transmitted, or course corrections being made, or even structural changes as dormant systems wake up. Or we might see nothing. If the probe is designed to remain covert, to study without interfering, then it might continue to masquerade as a comet, even as it carries out its mission. We'd never know it was there unless we got close enough to examine it in detail, close enough to see through whatever camouflage or protective coating it wears. This is all speculation, obviously. Wild speculation, the kind of thing that makes traditional astronomers uncomfortable. But it's useful speculation because it helps us think about what to look for. What would be the signatures of artificiality that we should watch for? For instance, if 3I divided by Atlas were natural, we'd expect its outgassing to be somewhat random and irregular, responding to solar heating in ways that are complex but ultimately predictable given enough data. If it's artificial, we might see patterns in the outgassing puffs of gas released at specific times or in specific directions, perhaps as a form of attitude control or propulsion. If it's natural, its trajectory should be determined purely by gravity and whatever small forces result from outgassing, the so-called rocket effect that caused Oumuamua's non-gravitational acceleration. If it's artificial, there might be deliberate course corrections, small changes in velocity or direction that can't be explained by natural forces. If it's natural, it should be electromagnetically quiet, except for the expected emissions from ionized gas in its coma. If it's artificial, there might be radio signals or laser pulses, attempts to communicate or gather data. None of these signatures have been detected so far, but we're looking, and we'll keep looking, as perihelion approaches. And honestly, even if 3I divided by Atlas turns out to be completely natural, even if we eventually figure out that the energy phenomenon is due to some exotic but understood plasma physics process, it will still have been worth the speculation. Because asking these questions, taking seriously the possibility that we might encounter something extraordinary, is how we prepare ourselves for a future that we know, statistically, must include such encounters eventually. Think about the numbers. There are an estimated 200 billion to 400 billion stars in our galaxy. If even a tiny fraction of those stars have planets, and even a tinier fraction of those planets develop life, and even a tinier fraction still develop intelligent life, and even a tinier fraction of that develops technology and survives long enough to send out interstellar probes, the number still might not be zero. And if the number isn't zero, if there are other technological civilizations out there, or even if there were in the past, then sooner or later we're going to find evidence of them. It might be a radio signal, it might be an artificial structure on an exoplanet that we detect through telescope observations. It might be ruins on Mars or the Moon, left by visitors millions of years ago. Or it might be something like 3I divided by Atlas, an object passing through our solar system that turns out to be more than it appears. We need to be ready for that possibility, intellectually and philosophically. We need to have thought through the implications, considered the possibilities, so that when the moment comes, we can respond thoughtfully rather than reactively. This is part of why SETI exists, why researchers spend time thinking about these scenarios. Not because they're likely to happen tomorrow, but because they might happen eventually, and preparation is worthwhile. So while we wait for more data on 3I divided by Atlas, while we watch it approach the sun and prepare for perihelion, we're also engaging in a useful exercise in preparedness. We're practicing what it would be like to encounter something genuinely unknown, something that doesn't fit our existing categories. And we're learning that even with our sophisticated instruments and our deep understanding of physics, there's still room for mystery in the cosmos. That's actually a comforting thought, in a way. Despite all our technology, despite all we've learned, the universe can still surprise us. It's still bigger than our models, stranger than our expectations. And that means there's always more to discover, always more questions to ask, always more frontiers to explore. In the coming weeks, as 3I divided by Atlas reaches perihelion and the energy interaction, whatever it is, reaches its peak, we're going to learn something. Maybe it'll be something small, a minor refinement to our models of comet solar wind interactions. Maybe it'll be something bigger, a new phenomenon that requires rethinking aspects of space plasma physics. Or maybe, just maybe, it'll be something that changes everything. Something that forces us to confront the reality that we're not alone in the universe, that intelligence and technology have been out there longer than we've existed. Whatever happens, it's a privilege to be alive at a time when we can observe it, when we have the tools and the knowledge to recognize when something strange is happening and to investigate it properly. Our ancestors saw comets and trembled with superstitious fear or awe. We see them and feel a different kind of awe, one informed by understanding, but no less profound. We know what they are, or at least we think we do, and yet they can still surprise us. 3I divided by Atlas is out there right now, moving through the dark, drawing ever closer to the sun's embrace. It's been traveling for eons, across distances so vast that light itself takes years to cross them. And now it's here, in our little corner of the galaxy, doing something that makes us question our understanding of how the cosmos works. In a few weeks, we'll know more. The data will come in, the models will be refined, and the mystery will begin to unravel or deepen. But regardless of the outcome, this moment of genuine cosmic uncertainty is something to be treasured. We're standing at the edge of the unknown, looking out into the dark, wondering what we're about to discover. And that feeling, that mixture of curiosity and anticipation and humility before the vastness of the universe, that's what being human in the age of exploration is all about. The sun continues to pour out its energy, as it has for nearly 5 billion years. The solar wind continues to blow, carrying with it the sun's magnetic field and the charged particles that fill the space between worlds. And 3I divided by Atlas continues its journey, a visitor from the depths of interstellar space, temporarily passing through our neighborhood before heading back out into the eternal night. Whether it's stealing energy from our star through some unknown process, or simply interacting with the solar environment in ways we haven't fully understood yet, it has captured our attention and our imagination. It has reminded us that the cosmos is full of wonders we've yet to comprehend, that the universe is not only stranger than we suppose, but stranger than we can suppose. And in doing so, it has given us a gift. The gift of mystery. The gift of wonder. The gift of knowing that there are still discoveries to be made, still questions to be answered, still cosmic puzzles waiting for curious minds to solve them. So, let's watch 3I divided by Atlas as it approaches the Sunday. Let's gather our data, run our models, test our theories. Let's be open to the possibility that we might be witnessing something unprecedented, something that will be remembered and studied for generations. And let's hold on to that sense of wonder, that feeling of standing before something vast and strange and beautiful, because that feeling more than any specific fact or figure is what drives us to explore, to question, to reach beyond our current understanding in search of truth. The cosmos is calling, and we, through our telescopes and spacecraft, through our calculations and theories, through our endless curiosity and our willingness to embrace mystery, are answering that call. This is the Sleepy Cosmos, reminding you that the universe is vast and strange and wonderful, and that sometimes, when we least expect it, something comes along that makes us realize just how much we still have to learn. The stars are waiting. The questions are waiting. And somewhere, out there, in the dark, Other mysteries are already making their way toward us, carrying with them the promise of future discoveries, future revelations, future moments of cosmic wonder. All we have to do is keep watching, keep wondering, and keep asking questions. The universe will do the rest. Thank you for joining me on this journey to the edge of the unknown. Until next time, keep looking up. The cosmos is full of sleepy secrets, and we've only just begun to wake them.